A spacecraft leaves Earth and moves toward the planet. The spacecraft moves at speed 0.6 c relative to the Earth. The planet is a distance 12 light years away according to the observer on Earth. A. Determine the time in years that it takes the spacecraft to reach the planet according to the observer on Earth and according to the observer in the spacecraft. First of all, this 12 light years it's a proper length. Why? Because by definition, the proper length is the length of the object measured in the reference frame where this object is at rest. So the observer relative to the Earth will measure the proper length, and it's 12 light years because it is given directly that 12 light years is measured according to the observer on Earth. But the observer in the spacecraft will measure the contracted length because this length is moving relative to the spacecraft, and this distance is L0 divided by gamma, where gamma is 1 over root 1 minus v squared over c squared, and it's 1.25 for v to be 0.60. And the observer in the spacecraft will measure the proper time. Why? Because by definition, proper time is time measured in the reference frame where events occur at the same place. Let the observer in the spacecraft be at the origin of this moving reference frame, and this observer turns on a clock when this reference frame is at the Earth, and this observer turns off a clock when this moving reference frame is at the planet. But this observer is always at the origin of the moving reference frame, so this observer is always at the same place. So two measurements of time are made at the same place. So this observer in the spacecraft in the moving reference frame measures the proper time. Is denoted as delta t0, t0, but the observer on the Earth will measure the dilated time, gamma delta t0. So relative to the Earth, time can be calculated as distance relative to the Earth. It's 12 light years, but what is a light year? If you multiply it by speed of light, c, you get the answer to be in years. So 12c divided by speed 0.6c becomes 20 years. And relative to the observer in the spacecraft, it can be calculated as distance relative to the spacecraft. It's 12c divided by 1.25 and also divided by speed, and it becomes 16 years. And also you can see that if you have calculated time relative to the Earth, it's what? It's dilated time, and time relative to the spacecraft is the proper time. So this time can be calculated as 20 divided by gamma, because we need proper time, and relative to the Earth we need the dilated time, and it's 16, it's proper time multiplied by gamma. The next, the spacecraft passes a space station that is at rest relative to the Earth. The proper length of the space station is 310 meters. State what is meant by proper length. The proper length is a length of the object measured in the reference frame where the object is at rest, or the length of the object measured when at rest relative to the observer. Calculate the length of the space station according to the observer in the spacecraft. So the observer in the spacecraft will measure the contracted length, and it becomes 310 divided by 1.25, and it's 250 meters. F and B are two flashing lights located at the ends of the space station as shown. As the spacecraft approaches the space station, F and B turn on. The lights turn on simultaneously according to the observer on the space station, who is midway between the lights, so somewhere here. State and explain which light, F or B, turns on first according to the observer in the spacecraft. So, first of all, we should know the next, that two events in the same point at the same time will be simultaneous for all inertial frames. And two events, arrivals of light or arrivals of signals from F and B by this observer on the space station, who is midway between the lights. These two events will be simultaneous for the reference frame relative to the space station, and they will be simultaneous for all other inertial frames, including the reference frame relative to the spacecraft, and all other reference frames must agree this fact, that arrivals of signals from F and B by the observer on the space station must be simultaneous. And notice that two events must be at the same time and at the same point. It's not enough two events be at the same time. They must be also at the same point. And for the observer on the space station, who is midway between the lights, arrivals of light signals will be simultaneous. And speed of light is constant for all, but relative to the spacecraft, space station is moving in this direction, and emitted light from B will pass a longer distance. It looks like this observer moves away from emitted signal, and hence light signal, or just light, or just signal, light from B will be in transit for longer time. But to be received by this observer simultaneously, B must be turned on first. So B turns on first. That's all for this question.